first talk will be given by Professor Tengfei Luo. I'll quickly introduce him. Tengfei is a professor in the Department of Aerospace and Mechanical Engineering. His research focuses on exploring the chemistry, conformation, properties, relationships of polymers using molecular simulations, machine learning, and experiments. This presentation is titled Artificial Intelligence Optimizes Additive Manufacturing of Thermoelectrics.
Thank you very much, Subhash, for the introduction, and also thank the organizers for the invitation. I'm Tengfei Luo. I'm a professor from Aerospace and Mechanical Engineering. So I'm actually presenting on behalf of a project team, not necessarily result from my group. So all the results shown here are from the team as a whole. Most of the work is actually done by Professor Zhang and Professor Daolin's group. I know Professor Daolin had a presentation this morning on a different project. So I'm just a speaker, right? So this is an energy research symposium. That's why I pick up a topic related to energy. So energy crisis has been a keyword for the past 2 decades. But energy production using fossil fuel is the single largest source of greenhouse gas emission and also pollution, as we know. Right? So if you have visited some third world countries, you see the air pollution is really bad mostly because of the power production. So we are all dreaming of energy future like this, right? But the reality is, still up to now, the overwhelming majority is still from fossil fuel of different kinds, okay? Be they oil, gas, coal, and then, so we're going to stuck with many of these power plants for quite a while. And unfortunately, we have many of these in the United States as well as in the world. Okay? Actually, this is for power generation, power plants. An equally big problem is from the transportation factor, like the cars we're driving. So if I tell you that the state-of-the-art power plants has an efficiency of 30 to 40%, you would think that's not terribly high, right? 30, 40%, and then you have 70, 60% waste. You would definitely not like the efficiency of the transportation sector, which is about 20%. So if you look at this pool car, and it's kind of small, I highlight the lost in terms of thermal energy is about 60%. Okay? And also, if we look at the national scale, we consume about 100 quads of energy yearly. I think there may be a top higher, not sure because of the pandemic, but around 100 quads. Then what is quad? One quad is 1 times 10 to the 15th BTU, British thermal unit. Yes, I'm a standard international person, so I need to remind myself that it's English. But anyway, 1 BTU is about 1,000 joule. And then, out of the 100 quads, we have about 67.5 quads that is wasted. That's about 60%, okay, 66%. And majority of it is actually wasted as some kind of heat. Okay? And there's not much we can do. So United States is a heavily industrialized, advanced country, and these thermal systems has been improving over the past 100 years, and really there's not much room we can do any better, okay? So since this is governed by the second law of thermodynamics, there's not much you can do. But if we can reuse some of this waste heat, say even if we use less than 1%, 0.75%, we would have approximately 0.5 plus, and that would be more than enough to electrify the state of India for a year. So we don't need much, we just need a little. So a very attractive technology for waste heat recovery is solid state thermoelectrics. Okay, there's no working fluid, and there's no moving parts. Okay, it leverages the universal phenomenon that particles would like to diffuse from a hot region to a cold region. Okay, and in this case, these particles are electrons or holes. So these are charge carriers. So when they are subject to a temperature difference, the holes and the electrons will move in one direction. Okay, and then you can link a load to these two legs, and then you can power a load. Okay, so that's power generation. A real thermoelectric module would look like this. Okay, you can buy it from Amazon. Actually, I'm teaching senior design. Every group of my students are buying this for cooling and heating of their experimental systems. And the most popular material is so-called bismuth telluride. Okay, the performance of this material described by this very complicated figure of merit ZT. Okay, it has a lot of parameters, and part of it we call it the power factor. Keep that in mind. We're going to discuss that more. So the figure of merit ZT of this state-of-the-art material has been improving for the past 7 decades, okay, by 50%. 50% in 7 decades, okay? And actually, about 15 years ago, all the major auto companies were looking into this thermoelectric technology and trying to recover part of the waste heat, okay? And then they have prototypes put on the CAT converters. That's where the heat has to go through. And then also, such technology has been researched for, say, power generation as well. What's limit their large-scale development? That means they have not been large-scale developed. It's one of the major factors is the manufacturing, right? So the conventional bulk material-based manufacturing is like this, okay? So you have the thermoelectric materials in powders, and then you synthesize it into ingot, and you dice them, and you assemble them into a module, and then here's what you can buy, mostly, all right? It is very time-consuming to fabricate this, and you use more materials, okay? And it has a lot of materials waste because you keep cutting them smaller. And assembly also has some challenges because the adhesion with electrodes. But the good thing is, we know it has been optimized for 70 years. It has the state-of-the-art efficiency. All right? One of our team member, Professor Yan Zhang, also from Aerospace Mechanical Engineering, is working on an additive manufacturing technology to build thermoelectrics from bottom up. Okay? It uses less material, okay, because there's no material waste. You're not cutting anything. There's no assembly needed because you print it. And if you're able to maintain the relatively high materials efficiency, you should be, say, looking at significant increase in the power density and over 90% reduction in terms of the cost. Okay. The previous speaker talked about the entrepreneurship. Right? Everything boils down eventually to the cost. So this is also any technology, eventually, it's about cost. But I said, if this material also has the same efficiency as those bulk materials. But that's a big if. And that is actually the largest problem. So by printing it, you get good material, but the efficiency is much lower. So as previously said, it took about 7 decades to optimize the bulk thermoelectric material. And now we need to optimize the printed material. Obviously, we don't want to spend another 70 years to do so, right? So the printing process looks very easy. Okay, so you put the thermoelectrics and make them into, say, small particles, nanoparticles, and you make them into inks, and then you put it into an inkjet printer and you print your device. Looks very easy. But optimizing this process is not trivial, because there are so many knobs you can tune for each step of this process. Okay, but in recent, we're definitely not going to use our brain to, say, explore the large parameter space. Okay? And then in a recently funded DOE project, we have a team, including 4 professors from Notre Dame and 1 scientist from Idaho National Lab. We started to develop a data-driven artificial intelligence algorithm to guide the optimization of the manufacturing process in order to quickly improve the thermoelectric efficiency. Okay, so what we do is we collect data from this printing, and then we train a machine learning model. Okay, we train a machine learning model based on the data, and then we use a method called Bayesian Optimization to guide us. So how to tune the process parameters in order to manufacture better thermoelectric materials. Okay, and this happens in an iterative manner until we can no longer reach, we can no longer further improve the efficiency. Okay, does this work? Right. So this is a glance of the result. I'm going to talk in more details in the following talk. So as a starting point, we choose only a few of these optimization parameters, more specifically on the sintering process, which I will talk about later. And within a few months, we were able to improve the so-called power factor, which is a factor in the field of merit, by 400%. Okay, so that didn't take decades, took a few months. So more importantly, according to the experimentalist, okay, they said some of these process parameters are very counterintuitive, predicted by the machine learning algorithm. So they would not usually go to that region to explore, but the Bayesian optimization was able to guide them to there and achieve much better results. I guess this is the value of resorting to machine learning. Okay, they can see something non-linear relations that we, using our bare eyes, cannot observe. All right, now let me tell you more details of what we did. Okay, so first, let me introduce the additive manufacturing method they're using. That's called aerosol jet printing. Okay, what they do is they have these nanoparticles suspended in some kind of fluids, and then atomize it, and then there will be a flow that carry the atomized nanoparticles to the printer head, and there will be a sheath flow that focus the flow to very tight spots, and then you can print whatever pattern you would like to print. Okay? So this process, this AJP process, is very versatile, and you can print thermoelectric materials, you can print sensors, and you can even print on organic substrates, like this is a leaf, and you can print on irregular shapes and also dedicated surfaces. Right, it's very versatile, but there's one thing. When we print these nanoparticle inks on the substrate, when they dry, they're still like particles, okay? Which is not good for transport. If you think about transport, You have electrons going from one place to another. You have heat going one place to another. If you see these boundaries, they get scattered. They cannot efficiently across the boundaries. Okay? So that's why for all of these materials, you need the so-called sintering process to eliminate the boundaries. So here I give you two examples. One is bismuth telluride based, which is the state-of-the-art material. The other is the silver selenide based material. So on the left, it's as print material, and on the right, it's after sintering. So usually, how people do sintering is put in the oven, bake it, like you bake a cake, for a few hours, and then hopefully the solvent would evaporate, and the grains will grow, and then they merge. Then obviously you can think this is much better for transport than this one, right? Because it has a lot of interfaces. Okay? So sintering is a key step to improve the efficiency of your printed material. So I said put it in the oven and bake it for a few hours. That's one way of doing the sintering. It's not high throughput. It takes time and it takes a lot of energy. But there is another way to do sintering, and it's what Professor Yan Liang's John's group is doing. It's the so-called intense pulsed light sintering. What it does is instead of using the oven to provide the heat, it shines a light. And the light, of course, the light intensity is very high, and you can locally heat up the sample, the film, and then the same thermal process happens. Okay, boundaries merge, solvent evaporates, and then we hope that we can get the same result as thermal sintering. Right? So this is a glance of their like xenon light, pulsed light sintering system. And there are at least 4 different knobs you can tune on this machine. Okay? And these include voltage, pulse duration, number of pulses, and pulse delay time. It's already a large optimization space, right? So think about if we want to do this in an exhaustive way for optimization, we can take 10 points on each of these parameters, and that quickly build up to, say, 10,000 experiments that we need to do, right? So this is too large for them to do the experiment, so we hope artificial intelligence will be able to help us. So to optimize this process, we used it to sinter the so-called silver selenide film, and this film has the efficiency is not as high as the state-of-the-art bismuth telluride, but it has certain advantages, such as non-toxic, and it's more mechanically robust. So this is the procedure we do the iteration. Okay. So this is an iteration among the thin film fabrication, and then the sintering, and also property measurements. Okay, in order to measure the thermoelectric property here specifically, we're measuring the power factor. And then we feed the data into the AI algorithm and use Bayesian optimization to guide us what we should do next in order to improve the thermoelectric property. Okay? And this is an iterative process until we can no longer see much better results. Okay? So in order, as I said previously, previous page, we have 4 parameters we can tune. Okay? In order to, say, model the relationship between the process parameters and the power factor, which is the target property we're optimizing, we use a machine learning model called the Gaussian process. Okay? It's a kind of machine learning model. And then we use the collected data from the experiment to train the model, and then use it to predict what would happen if we change the process parameters. Okay? And then combining the GP model, the Gaussian process model, with the Bayesian optimization, we'll be able to gradually improve our accuracy and also the target property. And then we hope to improve in this way. And this is a page where I introduce the Bayesian optimization. So the GP model actually works with the Bayesian rules with appropriate acquisition functions. Okay, so acquisition function you can think of objective function in your optimization process. Okay, to predict what process parameters should lead to better, say, thermoelectric properties. So here is an example of how Bayesian optimization works. So imagine we're trying to find, say, the maxima of this function, which is indicated by the dotted red line. The dotted red line we don't know, okay? And then, but we have some data collected at different conditions, and we know our experiments always have some uncertainties, right? So they may not fall on that dotted line exactly. So the good thing about GP model is that you can take into consideration of that uncertainty. Right? So this blue shaded area is 95% confidence of the GP model. Okay? It would predict the mean function as well as its errors. Right? So now we're trying to find the maxima, but we want to collect more data in order to learn this dotted curve better, right? But we don't know this dotted curve. That's where the Bayesian optimization comes in. Where the objective function, which is the expected improvement, it can guide us where to collect the data in order to get the most important information so that we can find exactly where this curve is. Okay? Once we know where exactly this curve is, then of course we know the maximum. Okay? So in iteration 1, this is where the Bayesian optimization tells us to collect a point. Iteration 2, still around this area. Iteration 3, this iteration 5, it asks us to collect the data here. And the iteration 7, it has to collect the data here, and that turns out to be the maximum. All right, so this is a 1D problem. We can visualize in this parameter space. But for our optimization of the sintering, it's a 4-dimensional, actually later on become 5-dimensional problem. We cannot visualize that, but the idea is the same. Okay, we use Bayesian optimization to tell us where to collect more data until we find the maximum. All right. So I'm just going to show the result. Okay. So overall, instead of say doing 10,000 experiments, we only needed to do 37 experiments. Okay, with different sets of say process conditions. In order to obtain the uncertainty. Each experimental condition, we did 3 experiments so that we have some kind of error. And then experiment 1 to 22, so 1 to 22, it has a very thick film, and later on we find thinner film would elevate us to better thermoelectric properties. Okay, so in this process, we initially didn't consider the thickness of the film, but later on, it was revealed this is a very important parameter. So that's another good thing about GP and Bayesian optimization. It's as you learn, you can put more parameters into your optimization. Okay? And then eventually we're able to say get a power factor over 2200 with a ZT of 1.1. And this is the best you can find in the literature. Okay? And it was not based on a trial and error method other people are usually using. It's a more systematic, data-driven, AI-guided method. And we're able to beat whatever reported results out there. Okay? The paper is under review. So, of course, I'm not a pure data scientist. I still would like to know what happened after the machine tells us what to do. So just by looking at microscopy images, we're able to understand why we get better results. Okay? Initially, say, these are unsintered. Okay? If we unsintered film has a power factor of 100-ish. And then if we put a single pulse, remember we're using this pulsed light for sintering. If we put one pulse, and that power factor was able to improve to 800. But you can optimize a little bit, it wouldn't change that much. Until the AI tell us to use a certain set of conditions, how many number of pulses, each pulse, how powerful it is, what is the pulse duration. That's a unique combination of that. And we're able to, say, form a film that is much better than the original film. Right? Like this is fully dense, and the boundaries is not very obvious. So this is good for transport, charge transport, thermal transport. And then if we put our power factor in a perspective with respect to other work, as you can see, our power factor is higher than the best. And also, these people use the oven sintering, which takes hours. We take a few seconds. Okay? So this is a big success from our point of view. Of course, now with these optimized thermoelectric materials, we can do some interesting demonstration. All right? So what the student Mortaza, it's Professor Yanan Zhang's PhD student who actually defended his thesis yesterday. And then he fabricated the device, okay? And this device, it's used to recover body heat and generate electricity, okay? It's a small amount of electricity, but it's sufficient to power some sensors, okay? We're talking about wearables. We want to monitor our health, and then a small amount of power would be very useful. Okay, and the largest contribution from my research group, besides brainstorming with the progress, is this hand. Okay, I literally just found out yesterday this hand is from my student. That's why I put a big head of him here. But anyways, so it's a very energetic, collaborative teamwork. So with that success, we are extending this methodology to optimize other parts of the processes, including ink formulation. We also have some very good results I'm not showing today, and we're going to extend that into printing. Okay, so we're about 1.5 years into this project, and we still have another 1.5 years to go. Last but not least, I would like to express my great gratitude to Subhash and also Bob. Your heads are bigger than any of those I have shown because you are very important. This is a DOE-funded project. They breathe on our neck like every day. Okay, we are meeting monthly. We have reports quarterly, and they have very stringent go, no-go thresholds yearly in order to, say, continue funding. Last year, we meet our go, no-go, and now we are in the sprint to reach our second year to go, no-go. So it's a very dynamic, but very, I would say, a little bit depressing project. They give us big money, though, so I guess that's what they expect. Of course, I would like to, so Bob and Subhash, and also representing Energy Center, has give significant administrative support to our project. Thank you very much. Of course, we would like to acknowledge the funding sources from DOE as well. With that, I'd like to stop here. I will be happy to take any questions.
So a combination of the previous talk and your talk, with this heat transferring of energy, could you produce that into like a watch that could charge your phone and things like that?
Yes. Casio who had one of these watches. You can, if you think about, of course, not the Apple Watch. These are monsters for batteries. For Casio, those watches, a small battery can last years. It doesn't need a lot of energy. So I think there are companies looking at that. I don't know how successful they are. I constantly see demos, but I don't think I have found anything on the market yet. So people are definitely looking at that. Cool. Yes.
So for your process here, when you're going back and you were talking about in the future you're going to look at ink formulations and things like that, how do you ensure that the results that you've already found for previous optimizations will still hold? So for instance, that those characteristics that you've already found are best for one particular ink formulation end up being applicable to other formulations. So it goes.
Exactly.
It's not that they're,
we have to do optimization again. I think for different material systems, they have different transport natures and mass diffusion. Essentially, sintering is mass diffusion, right? Different composition will have different those features. We have to optimize it again separately or in a combined manner. Okay, so we can change different formulations of the ink as well as changing the sintering process simultaneous. Okay, maybe that would give us even larger improvement than doing separately. That's a great question. So for the first year, we're trying to set up the tool and demonstrate on a relatively simple problem. Now we're adding more parameters. Yeah. Good question. Yes?
Hey, thanks. I'm curious about your thoughts on like scalability, for the certain like really large applications, right? Like cars, power plants,
Right.
we're going to do recovery. What about the materials, like availability and?
Yes, that's a good question. Now, bismuth telluride material availability it's not as good as silver selenide. Okay. I think a lot of the materials are from China. You have supply and national security issues. So far, I don't think there's much problem with this. It's not defense related, but it's not the most abundant minerals, but it's also not very rare. You have enough availability. It's just the supply chain can be an issue. Silver selenide would be better than bismuth telluride. Good question. Yes, Brendan.
I had a quick question about the deposition process, right?
Yes.
So I noticed that you can use, I understand this, right, my 3D printing is a little bit fuzzy as it is, but the solvent, so you've got the solvent, the additive, and then whatever deposition material that you're trying to take out, correct? Does the solvent end up getting incorporated into that, or it can primarily use higher oil solvents?
Yeah, I think no, solvent is used to carry the particles. Okay, you need to have the right rheology, right viscosity for it to print well. Okay, I think they have used the water as a solvent, also ethanol as solvent. It's not something very exotic, so they got evaporated. They have to evaporate that.
Some of those, I mean, I noticed you have a list, like the black holes up there, and things like that, right? So
Right.
these organic compounds, which they ligate to many of these metals or these frameworks, they don't end up getting incorporated at all in the deposition process.
My understanding is no. Okay, if for example, some of these particles they need better bridging at the boundary, they would add something else to the ink. It's solvent. It's to my understanding, it's fully evaporated, and they want it to be fully evaporated. Yes.
I just wanted to know if you could comment on expanding using like Bayesian decision making for other systems, like beyond thin film depositions, and maybe like what is the barrier to applying it more broadly? Because it sounds like really cool, and that we should all be
It's
doing
very
it.
cool. I've always been, say, physics-based researcher until a few years ago. I think, okay, why don't I try data-driven? And this is one of the first projects we worked on, and it worked brilliantly. I'm not sure I was lucky or it's generally the case. If you have well-defined control parameters, process parameters, and if you have well-defined target parameter, you can always formulate a Bayesian problem, and you can do this. The bottleneck is still how fast you can collect the experimental data. Okay, like this. Although we're saying printing is high throughput, we still need a week to collect data, to collect a few data points. So that would always be the bottleneck. Calculation take a few minutes or seconds. Then as long your film deposition, I would think it would take a few hours or shorter, and I think that is well doable. And the other thing is you need to measure the properties. Measuring the properties sometimes it can turn out to be non-trivial as well. So it's not on the Bayesian, not on the data aspect. It's always on the experimental aspect.
And kind of a follow-up question to that is, like, you had like experiment 32 as your optimized parameters. So what standard are you using to validate that your
Right.
optimized parameters really are
Sure.
producing like the most efficient outputs?
We never know, right?
Okay.
Because you don't know every point.
Sure.
So on the points we have explored, this is the best. And if we rely on Bayesian optimization, further recommend points to us, we would not find better points. Okay, so that's where we stop. Okay. And we're pretty happy with this number.
No, it's great, yeah.
All right, thank you very much.